Hey everybody, so this is going to be a review of your collisions and momentum homework. So this is from 8.4, Conservation of Momentum. So let's get started. So if you wish to change the momentum of an object, so you're looking to change your momentum or delta P, what do you have to do to that object? Well, it needs to have an impulse exerted on it. Okay, so B would be the answer there. So exert an impulse on it because your change in momentum is equal to your impulse. Number two, the force or impulse must be exerted on the object from where? This force or impulse must be exerted from outside of the object, okay? Because we learned yesterday with conservation of momentum that if all of your forces are internal to your system or that there's no external forces, then your momentum is conserved. So what you start with, you're going to end with. So if we want to exert a force or something onto this object, then it needs to come from external of our system. 3. If no outside force is present, then A, there is no change in momentum. And that's how we get the idea of the conservation of momentum. Because when all of the forces, like I said, are internal to your system, then there can be no change in momentum possible. So what you start with, you're going to end with. Number 4, the force on the cannonball inside the cannon barrel is equal and opposite to the force causing the cannon to recoil. Again, this all stems from Newton's third law that says for every action there is an equal and opposite reaction. So the same force that is shooting off the cannonball is the same force that is recoiling the cannon. Okay, same exact force, just acting in opposite directions. So again, the same magnitude or the same strength of that force, but it's just acting in opposite directions. So 5, explain why the total momentum of a cannonball system is 0 after firing. Again, this comes from the idea of the conservation of momentum and recognizing that the force that is shooting off the cannonball is the same amount of force that is shooting off the cannon itself. It's just acting in opposite directions. So the forces that are causing the motion in this system is within the system itself. Okay, so when there's no external forces acting on the object, then the change in momentum is going to be the same before and after. Okay, so this is how we get this idea. All right, so if we think about the cannon and cannonball originally at rest, when something is at rest, then the velocity is equal to 0. And if the velocity is equal to 0 and we plugged that into our momentum, then we would find that the momentum for the cannon and the cannonball, again, they're two different objects, but they're held within the same system. So the momentum for the cannon and the cannonball is 0. Okay, so that's our initial momentum is equal to 0. So then the cannon fires the cannonball out, right? And let's call the cannonball moving in that direction the positive side, and then the cannon is going to recoil, and let's call that the negative, because velocity is a vector, right? It holds magnitude and direction. It holds them very important. So the magnitude and the direction of that right side cannonball, and then the magnitude and direction of the cannon itself recoiling back is going to be negative. So if we were to find the final momentum, or the final momentum after that, then we can take this positive momentum from the cannonball added to that negative cannon momentum, and we are going to find that the sum of those two things is going to be 0. All right, and again, it's all due to the fact that the forces are all internal to our system. So when there's no external forces, then your momentum does not change. So your initial momentum is equal to your final momentum. And these are the products of your mass and velocity. So your velocity is going to change, right? It was originally 0 and now it's some either positive or negative number, but the product of your mass times velocity is going to be the same for each. So that was a long-winded example, but if this doesn't make sense, just think back to conservation of momentum. All right, when momentum is conserved, then we say, all right, then your initial equals your final. So if your forces are acting internal to your system, like they are with this cannonball system, then we can say, all right, then we can apply the conservation of momentum. So what my initial momentum was should be what my final momentum is. Number 6, is momentum a vector or scalar quantity? So momentum, it's equal to P equals m times v. And v is a vector quantity, right? V is velocity. It holds direction and it holds magnitude. So momentum would also be a vector quantity because it holds direction and magnitude. All right. Again, think about that positive and that negative with the cannonball and cannon system. Number 7, is the following sentence true or false? The law of conservation of momentum states that in the absence of an external force, the momentum of the system remains unchanged. This is true. This is the law of conservation of momentum. When there is no external forces acting on your object, then the momentum of your system remains unchanged, which means your initial equals your final. Number 8, is the following sentence true or false? If a system undergoes changes wherein all of the forces are internal, such as an atomic nuclei going under nuclear decay, the net momentum of the system before and after the event is the same. This is also true. Again, the system is undergoing changes where all of the forces are internal to your system. So if they're internal to your system, then there's no external forces, which means that you can apply the conservation of momentum, which says, the net momentum before is equal to the net momentum after. All right, moving on to 8.5 with collisions, and we talked a whole lot about collisions yesterday. So answering number 9, is the following sentence true or false? Whenever objects collide in the absence of external forces, the net momentum of both objects before the collision does not equal the net momentum of both the objects after the collision. This is false. Okay, so when objects collide in the absence of external forces, the net momentum of both before and after should be equal. So we understand collisions because of the conservation of momentum. So the momentum that you start with before equals the momentum that you start out after with. So when a collision happens, we said, okay, we have this initial mass, we have this initial mass and velocity from both of our objects. So then the equal sign happens, or that collision point happens, and whatever was before for your momentum has to be equal to whatever was after. So number 9 is false. When objects collide without being permanently deformed and without generating heat, the collision is called a elastic collision. All right, elastic. So again, this is when we have these two carts that are coming together. This one's at rest, this one's moving in. So we have this collision, bang, and all that happens is that your momentum gets transferred from one cart to another. So the velocity gets transferred to that other cart. Okay, and that's all due to the conservation of momentum. So whatever you start out with, you need to end with. Again, it's the product of those two things. So number 10, we just answered. So 11, describe how the velocities of each of the billiard balls changes in the elastic collisions below. So just to throw out these carts again, so we have these carts happening. One is at rest, one is moving towards the other cart with a certain amount of velocity. They collide. bang. So all that happens is that the momentum from one gets transferred to the other, and the other one leaves with a certain amount of velocity there. B, we have a cart 1, cart 2, they both hold masses, they both hold a certain amount of velocity. They're coming towards each other. Collision, again, this momentum gets transferred to one cart to the other cart, so they both leave with the same amount of velocity in the opposite directions. C, so this one is moving pretty slow, this one's moving faster, so they have the slow amount of velocity, they collide. This one gets transferred with that momentum, it moves a little bit faster than what it started with. All right, so again, this all stems from the idea of conservation of momentum. And the conservation of momentum states that in the absence of external forces, what you start with for momentum, you are going to end with momentum. And these are all examples, A, B, and C are all examples of elastic collisions. Why? Because there's no deforming, so nothing is combining here, and there is no heat generated. So all that's happening is that this momentum is being transferred from one thing to another. Number 12, a collision in which the colliding objects become distorted and generate heat during the collision. This is called an inelastic collision. So inelastic collisions, when things get distorted, when when heat is generated. So we have one cart at rest, another cart coming in with a certain amount of velocity. There's a collision. They actually combine and get distorted here, and they move together as one. All right, so we have that final velocity there. All right, so this was a review of your homework last night. Again, it's from that guided reading. If this stuff still does not make sense, you need to study it. You need to look at your notes and ask me good questions so that we can all get good grades. All right, watch your next video on the egg drop stuff, and I will see you all very soon. Bye.